Hello, everyone. Today we are very happy to have Balint Virag, and he will talk about the directed landscape. Thank you, Balint.
Hi, everybody. Thank you for having me. It's actually great that I can talk to you guys. Well, maybe because of COVID, but I'm very happy. You know, I haven't been able to connect to this community, and I really wanted to for a long time. So what I'm going to talk about is a sort of random geometry, maybe different from the one you're used to. It just comes from first passage percolation. And everything that I talk about is a joint work with Duncan Dovern, who's my graduate student, but it's not U of T, Heinika, Jano Shortman, and Surav Sarkar, who are all postdocs at Toronto. Let me see. Okay, so when I talk about random geometry, I just want to do, you know, the absolutely the simplest thing you can do in the plane, which is just, you know, put some kind of IID metric, right? And the simplest way to do that perhaps is to just look at the z squared, the graph, and assign length 1 or 2 by tossing coins, and then you look at this defines a new metric. So the edges have new random max. This defines a new metric, and then you're just interested in the most basic questions about this new metric. Something like, you know, what is the standard deviation of a path if you go from, say, 0, 0 to n, or something like that. Right? So one thing that when you do simulations, you find is somewhat surprising, is that in order to get standard deviation sigma, you know, you have to go to the point which is roughly like sigma cubed. Okay, so pretty far away. So there is already a strange exponent 3, and then you look at how. So then you do draw geodesics, so shortest path between 0, 0 and sigma cubed, and you see what does this path look like. So. You know, unlike in other geometries, this path actually looks fairly straight. So it doesn't really look random when you look at it from far away. So if you look at how much, for example, it deviates from a straight line, then it's sigma squared, roughly. And so it suggests that you have to, if you want to understand this kind of geometry, you have to do a different scaling lengthwise and widthwise, and that's what we will be doing. Also, you will see that the distribution is not Gaussian, even on fairly small, short samples. You can see that this distribution is really, you can see how the tails are kind of, let me see, are different here on the left and here on the right, right? And that's actually the feature of this model. It's interesting because there are actually several conjectures in this area, and they're papers that resolve these conjectures, assuming that this limiting distribution is Gaussian, and that certainly doesn't look like it would be the case. So here is what do we expect. So this is just based on what we discussed, right? So you're looking at the random distance between 2 points, and you'll have to scale according to these parameters, right? So I'm gonna pick, so I fix one direction, V0. For us, this was say 1, 1. Then I'm picking 2 vectors, one that's parallel to this direction, and set its scale so that it's just to the right for us. And then there is another vector, which is hopefully not parallel, or it won't be parallel, we call that U. And there'll be also a scalar M, such that when you look at the distance in this new coordinate system, so you see the new coordinate system is based on the vectors U and V, right? But it's scaled differently in sigma and in the direction V and then in the direction U. And that one has to do with lengthwise, and the other one has to do with the transversal fluctuations. And so first of all, there's a mean term. You see the first one is m times sigma q t minus s. It just tells you those are the coordinates in the v direction, the t and s for the 2 points. You see there'll be a roughly sigma cubed, because the mean distance is still coming from whatever was the distance. On average, you expect it to be the same size as the distance in the lattice. So there's that midterm. And then there is a fluctuation term. And this fluctuation term depends on all these parameters, right? So it's x, s, y, and t. Its order is sigma, right? That comes from the standard deviation we discussed before. And then there is a smaller order term. Right? So that's the conjecture. That's the precise conjecture, say, about first passage percolation. So what we expect is that there is this L, which is this 4-parameter thing, right? Which depends on these directions. You just think of it as the distance in your rescaled box, right? So the width of the box is sigma squared, the length of the box is sigma cubed. And then it's also, the distance is also rescaled. This big mean term is subtracted, is a new geometry. Okay, so this LXS tells you the distance between point XS and YT. And we expect this geometry to be universal. There is a minus sign here, by the way. That's just because of classical reasons, because you usually used to pay attention to last passage percolation more than first passage percolation. So L will be like a distance with a negative sign. So minus L satisfies the triangle inequality. By the way, that just follows from this asymptotics, right? Because this satisfies, and then there is this linear term which just cancels when you do the triangle inequality. So that just automatic. And you see there is 1, 2, 3 scaling, right? So you see a sigma to the first power here, see a sigma to the second power here, and the third power, say, here. Right? So those are the 1, 2, 3 scaling parameters. And also in the experience is that if you take different directions V0, if the main directions are different, then you get independent limits. So this fact that you have to scale this thing in this asymmetric way is actually inherent in the model. There isn't really another natural way to scale it. And so this L is called the directed landscape, and I'm going to talk about it. That's what this talk is about. So the standard thing that we look at is called universality, which is basically a central limit theorem in various settings, which says that this limit directed landscape is universal. It doesn't depend on this very specific details of the model. So let me be actually more precise about what should not matter. So first of all, the distribution of the edge length shouldn't matter. It should putting 1 or 2. I just use that because it's simple, but you could put, say, various other distribution. Whether the model is discrete or continuous shouldn't matter. So if you prefer, like a random Riemann metric, you could do that by putting some Poisson process and changing the metric according to that, if you like. Now, more interesting, it actually, so it's a graph metric, right? So weighted graph metric, if you like. You could make the graph directed, and actually we believe that shouldn't matter either. And in fact, the only models that we can prove converges to this limit come from directed metrics, and they're not even exactly the ones I told you about. So one, say, you take the 2-dimensional lattice and you direct each edge north or east according to which direction they go. Now, once you have a directed metric, you can do shortest or longest paths, right? You can just, instead of trying to find the short way, you can look for a lot of cookies along the way. And that's last passage percolation. And certainly you can just change the sign. And finally, another thing you can do is, instead of looking at the longest path, you can take some kind of exponential average of path length. So you exponentiate the length, and then you sum and take a log. So that's called polymer models. And we have now various polymer models directed polymer models that converge to the directed landscape. So what should really matter? Certainly one thing should matter is that they're in 2 dimensions. I would love to do this in any higher dimensions, but we can't. There are not even precise conjectures of what the exponents should be in 3D. And it's important also that these distributions are not heavy-tailed, and in fact, the restriction is fairly strict. So we believe we need 5 moments for the thing to work. And another thing is that because we believe this to be kind of universal plane geometry, it should be present in many everywhere in the world, right? So I mean, just like Euclidean geometry, you find everywhere, even if you have a problem that doesn't start with specifically Euclidean geometry. There are many places where it's kind of lurking behind, and that's certainly the case here as well. So you take, for example, the simplest interacting particle system, which is tasep, and you just have particles sitting on Z, and they jump to the right at rate 1 as long as there is nobody there already. So that's a model that was introduced by biologists. I talk more about it, and it's essentially equivalent to random geometry. Something we're familiar with is Tetris, stuff falling from the sky and forming kind of an interface. How the interface growth is if you do Tetris without actually playing it, just watching it, then that should be also in this world. There's the Eden model, where you think about some kind of, petri dish, like a bacterial colony that grows on the lattice, and at rate 1, you always add the neighboring side. That should also have this kind of limit. There's 2 random Schrödinger operators, longest increasing subsequences in permutations, and random matrices, most mysteriously. So there is a lot of connections with random matrices, a lot we understand. I still think essentially we don't really understand the connection. So I really like this to be an applied area, by the way. And so here is a shortest path between, according to Google, between Thebes, which was one of the places of the Pythagorean school, and the Acropolis of Athens. And you see that this thing is kind of not exactly a straight line. There's some randomness by nature and humans, of course. Whether this follows this, KPZ or geometry distribution, that's a question. I think the answer probably is no, but it's very interesting. But I think there should be extensions kind of having to do with these 5 moments that it actually should follow. So would be really nice to go in that direction. Okay, so let me give you a short exercise. So let's see what happens if I take, just to give you a feeling of what this directed landscape is like. Let's say that you take the Euclidean metric, so just usual Euclidean distance, and scale it according to my scaling. So I gave you some scaling before, how you should scale the random metric. Now we just apply it to the most familiar metric of that you know. And this is really a high school exercise. So you just take a limit, and what you get is it's called stretch Euclidean metric, or actually I prefer to call it now the Dirichlet metric, because when you have a path where space is function of time, then its length is actually the Dirichlet norm. So here is what the norm is. So you get some funny norm, and we'll discuss what it's like, right? So what you get is the norm. So the distance comes from a norm in the sense that the distance of 2 points is, of course, depends on the difference of the points, and the norm is y squared over s when s is greater than 0, 0, if ys is 0 and infinity otherwise. So what you see is that let me see. So what you see is that there is an asymmetry, right? So y and minus y is don't have the same direction. So because of this distance is directed. So it's not an actual distance function, but it's a direct. But it still satisfies. It's not symmetric, but it still satisfies the triangle inequality. Also, it can take, in this case, plus infinity values. That just means that this coordinate y is a time coordinate, so you cannot go backwards in time. So you only have finite distance between points if time t is ahead of time s. What is it? Maybe the other way. And that sort of comes from subtracting this big term, right? And so they're forced to do that. And so you get this kind of directed metric in the plane, which is deterministic. Now, what is the directed landscape? So I'll tell you a bit more about it, but basically it's some modification of the negative of this directed metric, this Dirichlet metric. It's just that plus Tracy-Widom random variable. Now the Tracy-Widom random variable that you add just depends on the time difference with the scaling with the factor of 1/3. I mean the law just depends on that, and it's just by scaling. But of course they are coupled in some intricate ways. So for every four parameters here, you get a different Tracy-Widom. So it's some kind of random surface. It's continuous, very continuous. So completely continuous functions. There is no problem with defining it as at all in that sense. It's not the distribution, it's just actually a function satisfying the triangular inequality. And it has a random fractal structure, just like Brownian motion, except one that is related to the 1, 2, 3 scaling. So if you take a point and you define its sigma rescaling by rescaling space by sigma squared and time minus sigma cubed, then if you look at directed landscape at this sigma points p sigma and q sigma, then you just get sigma times the original landscape in distribution. This is in distribution as a random function from r to the 4 to the reals plus minus infinity. Okay. Now there is one thing. So just like Brownian motion has an independent increment, this process also has a certain kind of independent increment property. And basically to understand it, it's because time in some sense has this, because you can go backwards in time, there's a way you can compose between two time slices to get the straddle, the sum of these two times. So basically the hard part is to understand this just a single time increment from say time 0 to time 1. Of course, other increments are you can get by scaling or simply by shift, because there is also stationary increments. So this is the harder thing, this Lx of y, and I'll tell you a little bit about how where it goes. So here's Lx of y. This is something called the Airy sheet. Sometimes you can see how on the left, when x and y changes together, then you're sort of going on the ridge of this parabola. There's a stationary process that way. Now, if you x and y go far away, right, from each other, then you're sort of going down. That means your kind of negative distance is decreasing. So the cookies that you can get are fewer because you're sort of far away. Quite amazingly, if you add a parabola back to this, it will become stationary, which is a remarkable property. And the right-hand side is just a contour plot of this. Locally, this thing looks like, so almost every point has a neighborhood around which it just looks like a sum of two Brownian motions, the Brownian motion in x and the Brownian motion in y. So if you plot that object and do contour plots, you'll get something quite similar to the right in this picture. Okay, so what do we know about the direct landscape? So it's a limit of various last passage percolation models, including Brownian last passage. There are also some directed first passage percolation models that we can get. It's a scaling limit of tasep in a very specific sense I can tell you about later. And it is also a scaling limit. It also gives you the scaling limit of longest increasing subsequences in random permutations. And I will tell you a little bit about that story in the next slide. So this is called Ulam's problem. You probably all heard about. So you take a permutation of the numbers 1 to n, and you look at increasing subsequences. You think of that permutation as a sequence. You look at increasing subsequences of this sequence. So for example, if the permutation is 2, 1, 4, 6, 3, 5, one of the longest increasing subsequences is 1, 4, 6. Another one would be 1, 4, 5. So these are not unique, but they certainly exist. And Hammersley in 1972 identified this as somehow a random geometry problem. And because of that, the limit exists by Kingman's ergodic theorem. And then, so the question they're asking is, how long is the longest increasing subsequences? And Hammersley, it follows from Hammersley's work that there is a limit if you divide by square root of n. And then Loganov, Shepard, and Virag and Karov found the constant there, which is 2. And then it waited 22 more years to actually find the distribution. When you subtract that mean and you scale the right way, what will be the distribution? And this was called the Tracy-Widom distribution, which was already understood from random matrices at the time. It's the limit of the top eigenvalue of a Hermitian symmetric random matrix. And in 2002, Prehofer-Spohn also found a process that has this property. And I will tell you what this process is, but essentially what it corresponds to in our case is changing one of the parameters of L. So really the hard part was to make it into a 2-parameter thing. And part of the reason it's a hard problem is because the 1-parameter process has very nice formulas. And for the 2-parameter process, we still don't have any reasonable formulas as far as we can tell. So the description is going through something completely different. Okay, so let me show you a geometric way to think about longest increasing subsequences. It's not the same as Hammersley, but it will be better for this discussion. So you see you have this grid here on the left. And in the first column, I changed the second edge over here to orange and lengthened it, right? And then the second column, the first edge, and the third column, the fourth edge, and so on. So I encoded the subsequence into geometry. And then you can easily, and say, and apart from all the other edges are length 1, or you could even set them length 0, it doesn't really matter. And then you look in this grid and you want to see what is the longest path, okay, which is only going to the right and up and going from the bottom left corner to the top right corner. And it's very easy to convince yourself that this actually just picks you the longest increasing subsequence. And so the edges that you use are going to be those. So it uses the long edge on the second column. So that gives you the 1. It uses the long edge in the third column, which corresponds to 4, and so on, and then the 6. So that's one way to think about it geometrically. And another way to generate this kind of graphs is instead of picking them from a random permutation, right? So we chose these edges according to a random permutation, but you could also choose them according to an IID coin toss. So you're just going to toss a coin and decide whether the edge is long or short. You can set a parameter for that coin toss, but apart from that, it will be IID. Turns out these models are actually fairly close. There isn't that much difference. But this one is a little bit easier to analyze, and I'll tell you how. So Seppälin and Johansson, this is called, by the way, the Seppälin and Johansson model. It's Timo Seppälin who found that there is actually various beautiful properties of this model that allow you, for example, to determine the limit shape. And then Johansson analyzed it, actually finding the Tracy-Widom distribution also in this specific model. So you see the vertical edges, we'll just set them to length 0, and the horizontal edges will be, Bernoulli distribution with some parameter p. I don't know why binomial is there. So, and then here is the longest. Here is a longest path, upright path on the right. Okay, so the way there's an amazing way to analyze this thing is it corresponds to it, and it's given by the RSK correspondence. So the RSK correspondence was actually invented here in Toronto in the 30s by Robinson, and then Schensted Knuth actually improved it a lot. In fact, the person who improved the most is Green, who connected it to last message percolation. And so let me tell you what it is. So given this kind of array, which corresponds to the edge length, right, in this graph that I've drawn. So it's this binomial array, right? This tells you, for example, this is a 1 because that edge is there here long, right? You're going to define a sequence of distances, and you're always going to measure distance from the bottom left corner, like that. And W1 is just going to be the distance to the top line. Okay, so there'll be n is just the size of the n is just the number of lines. So that's not really, that's a fixed parameter, but y is a variable. And so y is going to tell you where on the top line you're going. Okay, so I think W1 maybe the blue line, I think here in the top. Okay, in this picture, yeah, that's the blue line. So W1 is simple. Now to define W2, you're going to define another kind of distance, which is instead of just taking one path, you're going to look at the union of two paths. Okay, but if you have two paths that uses the same edge twice, then you won't count that twice. And then you just maximize over that this distance, or the sum of the edge weights along that. And so W2 is defined by saying that W1 plus W2 should be just this kind of maximal distance along the union of two paths. Then you can do it in this case 1, 2, and 3. And so the blue, the orange, and the green corresponds to K, 1 path, 2 paths, and 3 paths. So the sum of blue and orange would be, say, the union of two path distance. So it turns out that when you do this, RSK is actually an almost sure bijection. So think of it as an infinite, so it's 3 infinite binary sequences. Then it sends it somewhere to some sequence space, to the image of the thing. But amazingly, you can reconstruct with probability 1 where you came from. And also it's another amazing fact is that these things are increasing or non-increasing. Yeah, so W1 is greater than or equal to W2 and so on. Actually, it's a good exercise. Proving it for W1 greater than or equal to W2 is actually pretty easy, but when I prove W2 greater than or equal to W3, that's not so easy. So I recommend that as an exercise. And so because this is a bijection, okay, you kind of expect that it takes uniform measure on these arrays, right? So if p equals 1/2, then this is essentially uniform measure on these infinite arrays, and it should take it to uniform measure into these non-decreasing sequences, and that's actually correct. And there is a proof. Not only it's correct, but you can prove it this way. We have recently published a proof that just goes along that way. So that sort of tells you that just because you start out from uniform measure, you get uniform measure. What's uniform measure on this kind of set? Well, it's basically non-crossing Bernoulli walks. So Bernoulli walks that are staying ordered. And so there's a nice way to put uniform measure, and you can understand this uniform measure through the Carlin-McGregor formula, because they're non-crossing walks. It's easy to switch them to non-intersecting walks, and then you have that formula. Okay, and there is another nice thing, which is that once you have these paths, there is a metric, which is sometimes called the RSK metric. or we call it the RSK metric, which is just defines a distance. And let me tell you how you define this distance. So if you want to now define, say, a distance between this point here and say, so this is again a distance on the same set. So you can go from somewhere in the corner here to some point up on the top line. So what you have to do is you're gonna say how much time you spend on the bottom line, and you can jump on the top line and the second line, and then you jump on the top line and spend some time there. So this is gonna be the target of your distance. This is your starting point. And so this is how you're allowed to go. You stay for a while on the first line, and then the second, and then the third, and then you sum the increments of the path along where you've went, and you maximize all possible ways to do it. And that's the RSK metric. Okay, is this clear? Yeah.
Yeah.
Any questions about that? Okay. And it turns out that no matter where you start, so X is a point on the bottom where you start, and Y is a point on the top. It has to be on the top line. The RSK is actually an isometry. So the original metric is the same as the RSK metric. This is a very nice term that is related to kind of Whitman transforms and things. By the way, by definition, it is true for X equals 0 because that's how we defined it. but it is also true for other X's. That's unusual.
Can I ask one question?
Yes, of course.
Yeah, so you are using this max to define the metric. So,
yes.
And they still satisfy the triangle inequality using max.
Well, there are actually, it turns out, well, this metric is only between the bottom line and the top. Okay? So there isn't really any triangles at this point.
Oh.
but in fact, there are quadrangles. You can take 2 points in the top and 2 points in the bottom, and there is a quadrangle inequality. It comes from the triangle inequality, and it does satisfy that. And with a reverse sign, because it's a negative sign, right? Because it's a max.
Okay, I see. Thanks.
Over in last passage percolation world, it's a usual thing, like here when you switch from last to first and so on, just signs just switch. So
I see.
yeah, so with the negative sign, triangle inequalities. Okay, and it holds for all X. So basically, you can kind of encode your distances between at least the top line and the bottom line into these non-intersecting paths, and that's the key to RSK. So we can understand it because it's a bijection, right? That gives you the probabilistic strength of the RSK, and it helps us because it's an isometry. It encodes the geometry. And so I give you, now it's just a little bit of hand waving here, some technicalities, but now you let sigma go to infinity. What's going to happen? So first of all, these non-crossing walks that we had, right? They become Brownian motions. And because we send both dimensions to infinity, it's not just going to be not going to be 3 Brownian motions, but actually infinitely many. So it turns out this object exists, infinitely many Brownian motions that are conditioned not to intersect, and you can understand them through determinantal formulas. And it is called the Airy line ensemble. Now, the way you imagine is these are kind of parabolas as drawn in here. And the Brownian motions are just kind of conditioned not to intersect. Well, what does it really mean? So one way to define it is this beautiful thing called the Brownian-Gibbs property, introduced by Corbin and Hammond, which is I say, well, let's say erase a part of the top line from say time 0 and time 1, and I show you everything else except that part, and you ask you what is the conditional distribution of the path that I erased between time 0 and time 1, given everything else. And the answer is it's just a Brownian motion. It's conditioned not to intersect anybody else. Brownian bridge, I guess, because I fixed the endpoints, but it's conditioned not to intersect anyone else. It's also true for other segments. So that's, by the way, there is also a beautiful conjecture whether this is unique. It's been open for quite a while. So from the RSK metric, which I described, there is actually a metric in this area line ensemble. And the way it's defined is a Boozman function. So Boozman functions are just distances from infinity. So you do this kind of line type last passage percolation that I showed you before, right? Where you pick up increments. But you have to go from a certain asymptotic direction. Okay. And so the distance in the ALE between X and Y, the point Y is just going to be where I go to. So there's just actually a Y coordinate in this axis. Well, I guess it should be, well, yeah, so that's the Y. And the point X is an asymptotic direction. And you know, like if you want to say where you have to start the kth line, how you take this asymptotic, you start at minus k over root 2x and k. Yeah, so that's sort of the, and then it turns out, you know, this asymptotic direction exists, at least in the Boozman function sense, and then you can define this distance. So quite surprisingly, you know, this distance actually is symmetric in X and Y, like switch X and Y, the same law. And that's, yeah, that's not very clear from this picture. Right? It's clear from where it comes from, but not from this picture. Okay, so I basically told you how, yeah, here is the xk, right? This is xk, you just take a limit. Okay, and this LXY, so this Airy sheet is actually this Boozman function distance in this limiting object. Okay, so how does this proof go? So you know, the convergence to the Airy line ensemble is essentially going through, we can compute everything, which is still kind of a very standard, very standard requirement. There are a few exceptions now, but mostly in this area, KPZ, we either know everything or we know nothing, which is that we know everything if we can compute things, and we all know very little if we cannot compute things. So there is quite a bit of this non-intersecting walks and determinants and so on to understand this Airy line ensemble. And then you can write things in terms of determinants, and determinants are related to orthogonal polynomials. Limits of orthogonal polynomials on the edge are written in terms of Airy functions. They're very classical stuff, and then that's why it's called the Airy line ensemble, because it's expressed in terms of determinants involving Airy functions. Okay, so that's a remark about the proof. Now, what we like to look at is, for example, what happens to the shortest path, right? So you have had this path from 0, 0 to sigma cos sigma cubed. What will happen to this? So it turns out it has a limit, okay, a scaling limit. It's a random path. So what I did is here is a graph of that and Brownian bridge, and I wonder if you can tell the distinction, which one is which. So of course, the first guess would be that it's Brownian bridge, and turns out that's not true. The scaling is completely off, and the Hausdorff dimension is off. So this path actually has Hausdorff dimension 4/3 rather than 3/2, which is the Brownian image of a Brownian, or the graph of a Brownian motion. This path is a function, right? Because there is time, you're not allowed to go back in time. So it will be, so space is going to be a function of time. So it's a lot like kind of objects, a random element of continuous functions from 0, 1, and starting at 0, ending at 0, just like a Brownian bridge, but it's a different measure. They're mutually singular, distinguished by their Hausdorff dimension, which is an almost sure property. I won't tell you which one is the Brownian motion and which one is the directed geodesic, which is the name of this limiting geodesic. You can guess. Okay, so let me tell you a little bit. Okay, a little bit about. Oh yeah, so just 1 second. Okay, so what happens in these hidden geometries? So well, there's long-lasting secreted substances, polymers, and so on. These are things that you expect to converge to these limits. I'll tell you a little bit about these. And one of them is called the KPZ equation. So this was an open problem for quite a while, another two solutions. The KPZ equation is basically the log of the stochastic heat equation. And one way to think about it is just, and it also gave the name to the area from Kardar, Parisi, and Zhang. And it's, by the way, the same Parisi who got the Nobel Prize in physics this year. So when you have a directed polymer, remember it's like an exponential average of path length kind of stuff, and there is a recursion for this distance. In this world, it's called the free energy. In terms of, say, you fix one endpoint and move the other one, right? So there is also natural time direction there and space direction. And when you take a simple scaling limit of this, you get actually a stochastic differential equation, and that's the stochastic heat equation. And the log of that is the KPZ equation, which is written like this. So KPZ equation is in this form. It's very hard to interpret. So in fact, Martin Heyer got his Fields Medal for making sense out of objects like this. But anyway, if you exponentiate it, the stochastic heat equation is not so hard to interpret. And so one of the theorems that I proved, and also Jeremy Kestel and Suraf Sarkar, who, by the way, my colleagues, they were sort of all working in secret, so they only found out the last minute, or they did the same thing, and proofs are very different. Is that this object also converges to the directed landscape, at least as a function of x and time. So this thing. And now another object is tasep. So what's tasep? You just have an evolving interface. So you can think of it this way, that the particles jump to the right as long as there is nobody there. The height function is just think of the particle as a function and integrate it, the location of the particles. So just partial sums of how many particles are up to this location. That's the black line. And then when the particle jumps, then these little V's in the back line turn into little wedges. So you can think of this as an evolution on this surface, that the V's turn to wedges at rate 1, or one-dimensional surface. And the KPZ fixed point by was this amazing result of Matetsky, Kostonar-Menick in 2016, that you can actually describe the scaling limit of this Markov process. And what we proved is that this is actually given in terms of the directed landscape, and not just with a fixed initial condition, what is the result of MQR, but actually in all initial conditions jointly at the same time. So how is it given in terms of the directed landscape? So if you start with some initial profile, think of it as an initial configuration of particles. So this is h0 of x, just the height function at time x, and this is already after you take the limit, the scaling limit. And then the profile at time t is just the distance in this random geometry from that initial profile. And how do you define the distance? Well, you just maximize. So you look at a0 of x and look at lx, right? So look at x0, location x times 0, and yt, add h0 to that, and take a supremum. So it's like a Hopf-Flex formula in this setting, and that's not an accident. So one thing that we proved with Surab is that when you do this, you can start with any upper semi-continuous function. This was already known, and this actually makes sense. But one amazing property is that at any time, arbitrary small times, you let this evolution happen, then you look at, so you get a random function. When you look at this, any segment of this random function in a compact set, is absolutely continuous with respect to Brownian motion. So you can start with some terrible function, and in no time you get something which is super smooth, but super smooth in the stochastic sense, right? It's absolutely continuous with Brownian motion with variance too. Okay. So it's quite an interesting world. And finally, I want to say two more things. One of them is mRNA, which you probably heard about. So I told you tasep came from biologists. The original paper was about traffic through a cell membrane. So stuff going through a cell membrane, and there's a channel, and there's traffic jams. So they're trying to model those traffic jams using that. But the same kind of thing has been applied to ribosome, which is this gadget that takes the mRNA and turns it into the proteins, and it's reading it and then going along, and then there isn't only one, there's several of them, so they form traffic jams, and actually these are quite well understood through tasep. So actually this area is applied to fairly high degree. Finally, I want to tell you one more thing before I get to the open problems, is that if you look at the longest increasing subsequence as a random function, right? So you had these, I don't know, what was it, 146 or something, but imagine it's a much longer one. And then you can graph this function, and you can ask what is the scaling limit of that graph after subtracting the light linear function and so on. And turns out it is the directed geodesics. So it's one of those pictures that I showed you. So the scaling limit of the longest increasing subsequence problem is solved through this limiting geometry of last passage percolation. So, okay, so I have maybe 2 minutes, and I just open for questions. So you take, there's the open problems here are a lot. I mean, the basic things are open problems. So any IID weight first passage model on z-square. So we don't have any of those for which we can prove it, especially the one I used for motivation. We have no idea how to prove what the limit is, even though we pretty much understand what the limit should be. Actually, this story is much worse. Like even if you want to do a law of large numbers for first passage percolation, so just that first term with the sigma cubed and t minus s, that's the limit shape. What is that m? What is that coefficient there? What is the linear growth? So there isn't any IID first passage percolation model where that limit shape is known. And not only they're not known, it would be really nice to know that it's uniformly convex at a given point. I don't think there is a single example where we know that it's uniformly convex at a specific place. Some average results, but nothing like that. I told you about these non-intersecting Brownian motions. There is a very nice uniqueness question. There is only one such measure. There is a half-planes problem, which is, let's say I tell you, take the direct look landscape and I cut it in half vertically. I tell you all the distances on the right and all the distances on the left. So this may be somehow familiar. Here, you guys do stuff like that in SLE. And can I weld the two things together? In a sense that now I know all the distances on the entire plane. The reason it's a hard issue is because, well, what you try to do is, okay, well, you have this path and you break it into pieces that go in the left and go in the right, of course. But then when you try to resum, it turns out the error terms are too big, so we don't really know how to resum. Okay, and the length and shape problem is actually one that there is significant progress. And so the simplest version is if I give you a shape, so I give you the function which is the directed geodesic, can you tell me what its length is? Right. So is the length a function of the shape? So a version of this was proved by Duncan Dovern, which is that if I tell you all the shapes of all the geodesics in the entire plane, then he says, okay, I can tell you what all the lengths are. So that's there's a little bit of progress in these open things. Okay, well, thanks very much. I'll stop and open up for questions.